My name is Sascha Herr from the Technical University of Darmstadt. I'm going to present the topic that was mentioned. Here we see a composite laminate which consists of 3 plies and already contains some damage. For example, we have already 3 interfiber cracks in the middle ply and 1 interfiber crack in the upper ply. And such a structural damage situation already contains some 2-dimensional line secondaries, which are often considered in literature. For example, here at all the crack fronts which exist, but also at the laminate edges due to the laminate edge effect. But there are not only 2-dimensional singularities, but also 3-dimensional point singularities. And some are marked by red dots. For example, here the 2 interfiber cracks are meeting each other in the interface. Now we are especially interested in these 3-dimensional point singularities and want to study their possible influence to the failure process in such a laminate. On this talk, I want to show that the scaled boundary finite element method can be such a method. Okay, first I want to talk about what the SBFEM, scaled boundary finite element method, actually is and how it can be used to solve 3-dimensional boundary logic problems. Then I will talk about the benchmark example which we used to show that it's a properly usable method, which is benchmark example of 2 meeting cracks in a homogeneous isotropic solid block. Then I will talk about the application of the SBFEM and compare the performance of an enriched formulation and a standard formulation. And before I close with a short summary, I will actually show some incremental energy release rates that we calculated. Okay, I start with the scale boundary finite element method and the introduction to it. The scale boundary finite element method actually is a semi-analytical finite element method, but it has a major additional requirement, which is the geometric scalability. Geometric scalability means that there must be a point, the so-called scaling center within your body, from which you can draw a line to any point on the boundary without actually crossing it. So we can actually see it here. And then in the next step, we can introduce a scaled boundary coordinate system with a scaling coordinate C running from the scaling center to the boundary, and a boundary coordinate eta, which actually runs along the boundary. The next step is the crucial one for the method, because we only discretize the boundary with 1-dimensional finite elements, but consider the problem analytically in the scaling direction C. The same procedure can be equally employed for 3-dimensional bodies, but now we have 2 boundary coordinates eta 1 and 2, and accordingly have to introduce 2-dimensional finite elements on the boundary. Mathematically, this means that we can use a separation of variables approach, as we can see it here, with finite element shape functions, n in the boundary coordinates eta 1 and eta 2, and 3 functions in the scaling coordinate C. To introduce this separation of variables approach in the virtual work balance, do the transformation to scale boundary coordinates and the partial integration over the boundary coordinates, then we get a differential equation system, which we see here, and a linear equation system. Convex C denotes the second derivative in C, E0, E1, and E2 result from the integration over the boundary coordinates. And so this actually is a crucial differential equation system of 2nd order, which can be solved with standard methods. This is the linear equation system, which is used to enforce boundary conditions. And here we have the additional parameter P. This actually results from the loading on the discretized boundary. Okay, so the differential equation system can be transformed into a quadratic eigenvalue problem and yields the following solution, with lambdas being the eigenvalues of the quadratic eigenvalue problem and the phi's the eigenvectors of the quadratic eigenvalue problem. This case then can be determined using the linear equation system. So concluding, the SBFEM has the following advantages. Only the boundary needs to be discretized. We have arbitrarily anisotropic material behavior, which we can model. The near-field solution directly is obtained from an eigenvalue problem solution, because this actually matches the standard asymptotic expansions, which are typically given for a crack in tip near fields. And the scale-bounded finite element method can be coupled with the finite element method if the corresponding shape functions are used on the boundary. But of course, there are not only positive sides, there's also a downside to the method. If we have large eigenvalue problems, we have a lot of computational time. And this especially occurs when we get singular gradients on the boundary mesh, because then we need a very refined meshing on the boundary, which increases the number of degrees of freedom, which increases the numerical effort for the eigenvalue problem. Well, to help this problem, we recently introduced a rich formulation for the scale-bounded finite element method, which I want to shortly present. Here we want to consider a pyramidal domain with its top being standing right above the squared center, and now we introduce here a crack and a scaled boundary coordinate system at the top, so that only the bottom of this pyramid actually has to be discretized. So up to this point, it is the standard procedure of the standard scale-bounded finite element method. But now we want to introduce conditional enrichment, and for this we introduce a two-dimensional polar coordinate system where the crack front means the discretized boundary, and also scale this polar coordinate system with the scaling variable c towards the scaling center. So we get this enrichment with the enrichment functions f and coefficients b, and these coefficients b have to be functions of the scaling coordinate c, and so we actually get also a separation of variables approach just as for the standard part. Okay, for the further steps, we use the plateau method by Abbott and co-workers to minimize an additional number of degrees of freedom which we introduce. That means that for all enriched nodes, only one set of enrichment coefficients is introduced. Then we only use high-order Gauss integration, as it has been sufficient for our purposes so far. And the enrichment functions that we use are actually the decomposition of the classical crack-tip field as given by Fleming. Okay, now we come to the benchmark example which we want to consider, which is the case of two meeting cracks in a homogeneous isotropic solid block. Okay, here we see this, and in this case, this can be typical boundary mesh which you can use with the scale-bounded finite element method. And these actually are the 6 resulting deformation modes which are associated to singular stresses for this configuration. So we have 2 crack opening modes, 2 crack shearing modes, and 2 crack twisting modes. And here we see the associated singularity exponents for these 3-dimensional deformation modes. Then we also see that for CO1 and CT1 we actually get values smaller than -0.5, which is associated to a singularity which is even stronger than the classical crack singularity. Okay, so we consider this case, and for our calculations we introduced symmetry planes for facilitating the calculations, so that we keep only 1/4 of this original geometry. And here at the gray faces we have symmetry boundary conditions, and these lines we would have the crack fronts, and these meet at this point, so that here in the back we actually introduce the scaling center for the scale-bounded finite element method. And this is how mesh that we finally used for this calculation looks like. Here we have the crack fronts marked by red. We have the crack faces marked by red lines. The red circles mark the enrichment, the enriched nodes. And there's the typical mesh we used. Now this is our pre-crack situation, which we considered, but if we want to calculate energy release rate, we also need a post-crack situation. And to derive this, we start with the pre-crack situation first. And actually it's not very easy to find the right pre-crack situation, so we did a simple assumption in the first step and assumed this kind of post-cracking. This red phase is the considered crack extension. And that is actually observed in the case of electronic chips when they show elimination at their edges, or at their edges and corners, Now, as this configuration is rather difficult to measure, we simplified it further to a triangle. And in this case, we have 3 crack fronts actually meeting, and so we need 2 scaling centers to describe 3-dimensional point singularities. And if we have 2 scaling centers, we also have to introduce subdomains in this example, and these subdomains are of wedge shape, and so this is one discretized boundary of the wedge shape. And for clarity, we can also look at it from the other side, because here we have our scaling center, and we see in the back the discretized boundary with the image nodes. Okay, now we want to take a short look at how the image formulation actually performs compared to the standard formulation. We want to look at the stress singularity exponents, which we can calculate. For the pre-crack situation, we see here the results obtained for the enriched SBFEM are the squared, the filled squares, and the filled circles are the results obtained by the SBFEM, and the lines are the actually converged values. We see that the enriched SBFEM converges very fast and shows very accurate values for already very small meshes, which are only 4 elements along the height. Okay, and this is the postcard situation, and here we have similar behavior. The enriched formulation converges very fast. And we also wanted to look at a complete boundary value problem. Here we see the postcard situation, the assembled postcard situation actually with the 2 scaling centers, and the situation is subjected to a vertical loading. And here we see the convergence of the displacements in the double logarithmic plot. These are the SBFEM results. This is the enriched formulation, and we see that we beat the SBFEM by an order of magnitude in accuracy. And for the relative strain energy, we are even better using the enriched SBFEM. Okay, now let's have a short look at some actually calculated incremental energy release rates. This is once again how incremental energy release rates are defined. You have to take the difference of the strain energies of the pre-crack and the post-crack situation and divide this by the newly generated crack area. And now we want to take the post-crack situation and give to the post-crack situation the displacements from the deformation mode CO1 of the actually pre-crack situation. And this results in such a plot. So on the boundary we have the deformation of the pre-crack situation of the deformation mode CO1. But of course here we have a different geometry and therefore an opening of the crack extension. And we also get it for the deformation mode CO2, for completeness. And here we see the calculated strain rates, calculated strain energies from the post-crack situation and the resulting incremental energy release rates for deformation mode CO2 and different ones for deformation mode CO1 and CO2. Okay, so I want to conclude. The scale boundary finite element method is actually semi-analytical finite element method with 2 further requirements, which are geometric scalability and also a linear problem formulation. But only the boundary has been discretized, and the problem can be considered analytically in a scaling direction. This results in a Cauchy order differential equation system of 2nd order, which can be transformed into an eigenvalue problem, which directly gives the deformation modes and singularity exponents. And in the case, if that singularities are present on the boundary mesh, the enriched SBFEM should be used. Okay, and using this enriched SBFEM, we considered the case of 2 perpendicularly meeting cracks with symmetry boundary conditions, so that we only keep 2 singular deformation modes, of which one actually is hypersingular, so stronger than the classical crack singularity. And as a post-crack situation, we introduce a triangular crack extension and calculated the incremental energy release rates. Okay, so thank you for your attention.